empty or well, okay, too late to worry about it. Okay, so here I'm just recycling notation. It's my notation. P from 1 to I will be the polygonal path, polygonal line, but I take from P only the first I vertices, just the prefix of the polygonal line. Okay, P from 1 dot dot 3 would be P1, P2, P3, just this polygonal line. Okay, same goes for J. Just recycling, abusing the notation of prefix that we just saw. And I need to tell you something about the two measurements that we are going to use, Frechet and dynamic time warping. So both belongs to a big class of measurements of curves called phi distances. Phi after the person-dog behavior. So what am I trying to say? I want to say that there is a dog that takes a walk on one of the curve, and there is a person that moves along the other curve. Let's admire Golda once again. Very photogenic here. Yeah. And the person over here, and each one is moving across the other part. And now, let's assume that the timing of each one is given. Where is the timing of each one at every moment? Somebody gave me a schedule at which are you at each moment. And what am I measuring right now? I'm measuring at every moment how far the person is from the dog. So I'll check at every instant how far away are they from each other, and they ask, does it mean that the two curves are close to each other or not? But this is a very confusing question because it's really depending on how fast the dog or the person moves. Like if they are moving coordinately, then presumably these distances should be close. These measurements that I'm giving should be close if they are coordinating each other. So let's try to be a bit more specific. I'll assume, so if I wanted to give me any meaningful results, I cannot assume that somebody gave me the schedule, because I'm asking how close the trajectories are, not how close the actual schedule is. It's up to me to decide what is the best schedule. So our problem is like a joint problem. Let's find a schedule that minimizes the distance between the curve. OK, let's try to be less hand-wavy. What is a schedule here? So I'll think about a sequence of discrete steps. I'll have to find what is this sequence, but I have a clock that says at every moment, every second, something should happen. What do I mean? At t equal 1, the person is right here, the dog is right here. Must be. When they terminate the walk, they are at the last vertices of their trajectories correspondingly. What should happen at every time step? At every time step, one of them, at least one of them must move. At every time step, at least one of them must move. Move where? Move to the next vertex. It's a discrete dynamic time warping. At every time step, at least one of them must move. It's possibly that both of them move. So at every time step, either the person moves, or the dogs move, or they both move. Move always means from one vertex to another. And at every moment, that is, once they landed and taking a rest for a moment on their vertices, I check the distance between them. At every instant that they stop, we measure the distance between them. We think about it as the length of the leash between them. And the best schedule is one that allows me to minimize the sum of leashes among all the time steps. The best schedule would be the one that allows me to fit the leash as well as possible. It becomes way too abstract. Here is P. Person is on P. And here is Q. Notice that by doing it, I'm also telling you what is the alignment, what is a matching of vertices of P to vertices of Q. It's not one-to-one matching, quite the opposite. I don't necessarily want to force it to be one-to-one, but there is a matching or alignment between where I was driving in P and what is a corresponding location in Q when I was driving along the same trajectory yesterday. So let's think about it. Person, dog. Dog is here, person is here, that's the length of the leash. P1, Q1. You don't have control about where they start, you don't have control about where they stop. What you have control is about who moves when. But moving is always to the next vertex, if they move. And it's OK if one of them stays in the same location. So what would be a possible schedule? Possible schedule would be, I'll take a break. It's me here. I'll take a break. The dog moves all the way up to here, but the dog can move only one step at a time. So I'll have to measure the length of the leash right here, and I'll have to measure the length of the leash here. The length of the leash, remember, I don't move in this schedule. The length of the leash from here to here, and so on and so forth. Many, many leashes all the way until the dog got to here. And that will give me some number, but that's a terrible schedule. It means we are definitely not coordinates with each other. Correct? And of course, the opposite, that as the dog stays and it's me that is moving, is completely identical. And what will be the time over here until we are done? If first the dog moves, and we said we are finishing up only when they are both on the end. So a possible and not very attractive schedule would be first the dog moves all the way until it reaches Qn, and then I'll move until I'll reach Pn, taking 2n time steps altogether and creating very, very long sum of leashes. If I want to find a good alignment between these two signals or these two trajectories, possibly it was, here's one application. Here is one path on the map, and here is my GPS location that don't align exactly, but are quite close to where the GPS, the location from the maps are. That would be a very popular and useful application here. How do I align maps? OK, so let's find a better scheduling that minimizes the total sum of the length of the leashes. As we said, first one, what I'm drawing in purple is the length, is the optimal leash. Here is one. We start over here. What happened in the next time step? I move to the next vertex over here. The dog moves to the next vertex over here. We both jump. Here is the next leash. What happened in the next time step? To minimize the total sum of length of the leashes, the dog should take a break, staying right here when I'm moving across all the vertices over here. Right? The dog should stay here when I'm moving across all these vertices. Again, summing up this length of leashes. Next, we both jump. Next, we both jump once again, and yeah. And that probably is the best. Oh, sorry, I forgot something. Then I'll take a break over here when the dog is the one that is moving throughout all these vertices. So it essentially, this minimum length of leashes suggested that all these vertices that I created here, because I was driving very slow, matches another vertex that happens when I was driving much faster. OK, it was a very, very long explanation into an algorithm that is going to be really short. People, do you understand me so far? OK, just to describe one of the many, many applications of dynamic time warping is that I'd like to do speech recognition, signature verification, but historically, vehicle trajectories, bird flocking, GPS location, stocks analysis, and so on, so forth. Really a lot of applications. And when you're using it, usually it will come with other constraints about what is reasonable length of leashes that could be useful. And it's very easy to inject more constraints into this basic algorithm, as you'll all see in the homework. But OK, what is our main theorem? And see how similar it is to the LCS case. I'll denote by Cij the cost of the dynamic time warping. Time warping, like, because I can make the time shorter or longer on one path corresponding to the other. So I'll assume that Cij is the optimum sum of lengths of the leashes under the optimum schedule, but where we both start at P1, Q1, dogman starts at P1, Q1, but we end only at vertex Pi and Qj. That is, here I'm thinking about the polygonal path, going back where it's like. Here I'm going on thinking about the polygonal path of the first I vertices of P, the first j vertices of Q, and Cij is a sum of lengths of the leashes after the optimum trajectory. And just as before, C11 in this case is what? We start at P1 and Q1. That's the length of the leash that we have to pay at the beginning. It needs to be counted. So C11 is just a distance. I'll denote it to you. I'll denote this notation for the Euclidean distance. The distance from P1 to Q1. C1i says what? I stuck over here, and the dog moving, but I cannot leave my location. That's the whole polygonal path. So C1i is just a sum of length of the leashes between P1 and every other vertex up to the I1. And you can do it in n squared. This just makes a bit a quicker summation of what is, how to initialize it. And similarly for Ci, 1. You have to pay the length of the last leash. What is C of I, 1? C of I, 1 will say if C of I, 1 means the dog is stuck at Q1. Dogs cannot move. It means that it's moving all the way up to Pi. What is the length of the sum of length of leashes that I have to pay? I have to pay this leash plus everything that I paid earlier, which is by now summarized by this term, the sum of the lengths of the leashes earlier, the C of I minus 1. OK, moving along. Let's think about what is Cij. What is Cij means we consider the case where the person is at Pi and the dog is at Qj. Do I know that in the optimum scheduling, the person and the dog will be at these locations? Absolutely not. I'm not sure that this is part of the optimal solution. But if it is part of the optimal solution, because the optimal solution consists of pairs of I prime, J prime, I don't know if this is a part, but if it is a part, if Pi and Qj happens to be the last vertices that I'm visiting, then what would be Cij? What would be the optimum scheduling, optimum alignment that brings me to a situation where Pi Qj is part of it? What do I have to pay? I'll have to pay the length of this leash and the optimum cost of everything that happens earlier. But how can I think about everything that happens earlier? What is the step that got me to configuration PIQJ? Well, I'm not sure, but there is only 3 options. One time step ago, either the I was at pi minus 1 and the dog was at qj minus 1, and then from this scenario to this scenario, we just both jumped. That's one option. Or another option is one step ago, I was already in pi, and it was a dog that jumped. Or the only other third option is that the dog was already in qj, and it was me that jumped. So last step, one of the 3 options, either they both jumped, or the dog jumped, or they both jumped. But they all can only jump over one vertex. See how simple it is after all this speech. For every I and j, Cij is the length of the leash between pi and qj. We're assuming that Cij is that the last step is the I and j. We're solving the sub-problem of matching the prefix of I characters, of vertices to j vertices. This is the last step. You have to pay the length of the leash. Now, what else do you need to pay? Everything that happens before, but before either they both jumped, and the cost that I need to pay for everything beforehand is just ci minus 1, j minus 1. Again, that was the optimum solution up to this case. And if I need to solve it for the I minus 1, j minus 1 problem, that's a solution that I will use. Or the person jumped from pi minus 1 to pi. The dog was already at qj one step ago. Or the alternative part. Which one is the best for me? Which one yields the optimum cost? The minimum out of only these 3 operations. And once again, I'm going to memorize it in a table, exactly the same table. And know that when I need this value, when I want to insert a value over here, these 3 values are already computed. That is, I need to increment I and j. I cannot go, for example, backward. OK, so here is the whole algorithm. You already saw the init. And the code is for I goes from 2 to n, j equal 2 to n. Cij is nothing but the length of the leash between pi and qj, plus the minimum of the 3 cells. Where are the 3 cells in the table? Here is cell ij. And what I need to look at is the 3 cells that are around it and take the minimum of this or this or this. And that's what I'll add Cij, and that's what I'll write over here. OK. And as usual, after I'll fill the table, I'll go backward. Next problem, Frechet. Frechet, again, assumes 2 polygonal paths. 2 polygonal paths, the very same input, the very same dog, leash, Golda, me moving along, some schedule between us. But what happened is the dynamic time hopping. Let's assume that my input consists of P with a lot and lots of points around it, and Q with a lot and lots of it, but Q is straight, and they are very close. So the only difference between P and Q is one point that is somehow out of the way. But beside it, they are identical. Now, dynamic time hopping will say, oh, you have one outlier, one error message, one measurement error. Then since you are summing up the length of all the leashes, then we don't put too much weight on one particular error. Frechet, on the other hand, will say, no, 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 it's very important. It suggests that they are not the same curve. So we do want to pay attention to it. Actually, we want to ask, okay, not what is the sum of length of the leashes, but instead, what is a small short leash that I can use to do the whole trip successfully? Again, I will ask, what is the shortest length of the leash that I can use to do the whole scheduling successfully? Now, this problem of both find the scheduling and do the minimization of the length of the leash is really hard. To find both scheduling and minimum length of the leash as a one problem, it's too hard for me. So I'll divide it. I'll say, assuming some oracle came down to earth and told me the actual length of the leash that you need is 17. And my problem is to say, tell the oracle you are right or you are wrong. 17 is too short, or 17 is just long enough, and then maybe I can try a shorter leash. So again, I'll assume that my input here is P, just as before, Q, just as before, and target length of the leash, and the output that I want from this algorithm would be yes or no. Can I find the scheduling or not? And there is a different part here that more cleverly or less cleverly do some binary search about some values, and eventually said, here is an error measurement because the optimal length of the leash. Right? Because if a leash is too short, then definitely any shorter leash will not make it possible. And if the leash is long enough that making it longer will just give you the same answer. OK? So it's exactly like the dynamic time hopping, but now I'm asking for the maximum leash, and I just need a Boolean answer, yes or no. So and I want to show you inherently two solutions to it. So first, I'll create my array just as before, but now this array contains Boolean values. Cij now is not going to be the length of the leash because it's fixed. It's part of the input. It's just going to ask, yes, I can reach cell ij, or no, I cannot. So Cij is yes if I can reach the cell using only the length of the leash, that is R. Again, R over here, parameter, part of the input, 17. Try a leash of 17. Can you make it or not? What should I return as an output? I need to tell the user if this cell, the last cell, what is the last cell? Last cell asks, the person, just as before, is here. The dog, just as before, is here. Can I make the whole trip from P1, Q1 into Pn, Qn while using only leash of length R? Yes or no? Tell me what's written right here in this cell. Now, obviously, if the length of the leash over here, here is my length of the leash, this is R, much shorter. It doesn't even fit the starting condition. I cannot even place on P1, Q1 with this length of the leash. The answer should obviously be no. And the same hold at the end, if there are no. But the answer should be no also if your path looks like this. Right? So here I can do the length of the leash. At the beginning, the length of the leash at the end are all fine, but I cannot pass this bottleneck with this length of the leash. OK. Our main, our init of the array right now is, remember, the Frechet here in AMD different than the Frechet that you'll find online. The Frechet online just also give you the minimum length of the leash, but the algorithm works the same. Just you would not see the R as part of the input. So init, what is C11? It's a Boolean answer. I'm writing here, can I make it from P1, Q1 to P1, Q1? That is, I'm not moving it all. But can we even stand still with a leash of length, input leash, 17? Yes or no? What is a init? When I'm standing here, can the dog make it all the way with leash of length R without me moving at all? So Cij is just, can I make it all the way from PR to is pi minus q1, the distance between them, is a short enough leash. And in addition, it's Boolean, and you can make it all the way to pi minus 1, comma 1 recursively. Okay, and the same for the dog, completely analogy. Here is the main theorem. Very similar to the LCS, very similar to the edit distance, the same philosophy, just as before. What happened in the last step? The last step, if we got to PIQJ, then one step ago, either we both jumped, dog and person, or just I jumped, or just a dog jumped. These are the only three options. So Cij, answer should be yes or no. Can we make it all the way from P1Q1 to CIQJ? Now, if Pi minus Qj, if this distance is larger than R, then the answer is obviously no. As far as I know, it's the last locations. But if the answer is yes, this is Pi minus Qj, the distance between them is less than R, then maybe yes, but what else should I check? Could I get to any of the previous three steps? Is it true that Ci minus 1j is true? If yes, then great. Then I can make it all the way to PIQJ. Or possibly this is true, Cij minus 1, implying that I was already in Pi and the dog was the one that jumped. Or Ci minus 1j minus 1 is true. We both jumped. One of them must be true. Okay. I'll wait a second with this. We have 4 minutes, which I think is enough. Sorry. How did it go? That other usage of Frechet that we didn't get to today. Yeah, we made this video way back in 2002, 2003. Hello, it worked just earlier ago. Oh, I like, demos as usual. Maybe we'll give it one more try, and if not, then as okay.
Finding a Curve in a Map by Alon Efrat, Lingeshwaran Polanyapan and Carola Wenk from University of Arizona, and by Helmut Alt and Günter Rothe from Free University
I'll fast forward through a bit of the technical part.
Let alpha and beta be two curves in a plane.
Instead of P
A
and Q.
well-suited distance measure for curves is the Frechet distance, which is defined via continuous and monotone reparameterizations of the two curves. The definition can be visualized as follows. Consider the two curves, one blue and one green in this example. Now imagine a man walking on the blue curve and a dog walking on the green curve. Of course, the man holds the dog at a leash, which is the black line segment here. Both the man and the dog can control their speeds independently, but are not allowed to move backwards. Then the Frechet distance is the length of the shortest possible leash with which the man and the dog can walk their curves from beginning to end.
Exactly the same, except that here it's continuous instead of discrete. We are measuring the distance all the time.
Consider the following scenario. Eric goes on a hike in the mountains, and he records his coordinates during the hike with his GPS receiver. The sequence of Eric's GPS positions describes a polygonal path, and we would like to identify the hiking trails on which he traveled. Since the GPS technology is rather noisy, we cannot assume to find an exact matching. To abstract the problem, assume we are given a polygonal curve alpha which represents Eric's path of GPS positions, and we are given a road map which we model as a geometric graph G embedded in the plane with straight line edges. We wish to find a path beta in the graph G which has the closest Frechet distance to the GPS curve alpha. In our example, beta is highlighted in brown. The length of the black line segment in the lower right corner illustrates the optimal Frechet distance, or in other words, the leash length. Also notice that the task we are solving is a partial matching task, which consists of finding a subpath beta and G together with a schedule of the dog walking on alpha and the man walking on beta. In SOTA 2003, we presented an algorithm for this problem. The runtime of our algorithm is order n square log square n, where n denotes the maximum of the complexities of the graph and the curve. Observe that this is only one log factor slower than the computation of the Frechet distance between two curves, although we solve a more complicated partial matching task.
Now, why is this good
We'll
for?
now show some examples that have been obtained with the implementation of our algorithm. In this example, the curve describes a loop which runs close to a cycle in the graph. Hence, we find a path in the graph which includes a cycle. The black line segments show the mapping of points between the curve and the path. Notice that the man traverses the bottom edge twice. In degenerate cases, this can lead to traveling the same edge back and forth several times. Notice that this is not a violation of the monotonicity constraints in the definition of the Frechet distance, because we select a path in the graph which contains the same edge several times.
So that's why it's useful, I
parallel
think.
vertical line segments of the blue graph. Although the green curve is closer to the right segment, the man clearly prefers the left segment over the right segment because it allows a continuous schedule with a smaller leash length. This shows the advantage of using the Frechet distance, as opposed to distance measures like the Hausdorff distance, which are based on a local notion of similarity.
This is one block street, dead-end street. Presumably you walked on the other curve.
Free space diagram of two
Okay.
curves
That will come next, where we.
parameter
Okay, that will take. We'll wait for next class. But anyhow, since we had it, check publication about map alignment and Frechet, it becomes very, very common thing, very important in working with maps, aligning maps, improving your, not exactly Frechet, but it's basically said, here is the map and here is the signal for my GPS, but sometimes I need my car to navigate and it needs to know where they are. And if I don't have GPS signal at this very moment or low quality, I want to somehow estimate, and it's good that I have the map because I can align my GPS with what is most likely is actually my trajectory. Same way, if I study trajectories, like ways that I study trajectory by itself, it's one of the methods to improve my localization where GPS signal is weak. Okay, thanks everybody.